In this video, we're going to extend what we know about integrating trig functions to look at trig functions where they are in fact composite functions. So I've got my trig ratio or a product of trig ratios, and they are of another function. In this case, these examples will just look at a linear function. Let's just first explore a little bit. Consider if I've got the function a quarter sine 4x, and now I want to differentiate that function. Now we know that we're going to have to use the chain rule because my outer function is sine of an angle and my inner function is 4x. That quarter just comes out. So when I differentiate, there's my quarter. The derivative of sine of an angle is cos of that angle. Then chain rule says I go inside, and the derivative of 4x is 4. So if I simplify that out, I'm going to get quarter times 4 is 1, so I'm going to get cos 4x. So what I used here, what I used to get that is the chain rule. Okay. So now obviously we're going to go the other way around. If I had to integrate that, how do I land up back at that? So hence, if I want to integrate cos of 4x dx, I'm going to get a quarter sine 4x, and then plus my constant of integration. So we're looking at, if I've got a trig function that is in fact a composite function, I know that I'm going to integrate that function and also times it, if the inner function is linear, times it by 1 over 4. Actually, that's the derivative then of that inner function. Well, it's to cope with to get rid of the derivative of the inner function. So it's very important with these integrals, don't forget to multiply by 1 over whatever the coefficient of x is, 1 over a. So let's have a look at an example. And remember to keep looking back at your table. So actually I'm going to pop my table here, okay, just to help me. So if I am finding the integral of sec squared 3x, that is in fact a composite function. It's sec squared of an angle, which I can see here. So I know how to integrate that. It's tan of an angle. Then I need to take into consideration cancelling out the derivative of 3x, so I need to times by 1 over 3. So let's do that. I've got 1 over 3, and the integral of sec squared of an angle is tan of an angle, plus my constant of integration. Don't forget that that angle has to match. If there's a 3x here, there's got to be a 3x over here. Cool. Let's look at another example. Again, I'm just going to pop my table here so that I can use it. You should have yours next to you as you're working. Let's see, I'm finding the integral of cosec of an angle times by cot of an angle. Now that angle is itself a linear function, so I know that it's going to be composite. Let's see, have I got cosec of an angle times cot of an angle? Cosec of an angle times cot of an angle? I almost do, I just want a negative. So remember what we said in the previous video, we sometimes need to create that. So I'm going to create an instance where I've got the negative because I want integral of negative cosec to x times by cot to x dx. Let me just move this over a little bit, get some space, dx. I'm allowed to put that negative there as long as I compensate with the negative outside. So I know that the integral of cosec of an angle times cot of an angle is just cosec of that angle. But to compensate for the derivative of the inside function, when we go backwards, I need times by half. So there's my negative from outside. Then I've got half cosec 2x, and then plus my constant of integration. All right, let's try another one. Just drag my table down so I can use it. Cool. Let's look at this example here. I've got sec of an angle times tan of an angle, so I go look for that. Do I have that here in this column? Yes, I do. Sec of an angle times tan of an angle. Have a look at that angle. It is itself its own function. It's linear. Let me rewrite it for you so that you can in fact see that it's a linear function. So integral sec of a quarter x times by tan of a quarter x dx. So we know we've got to go 1 over that to compensate. That's 1 over a quarter, which we know is just 4. Sec of an angle times tan of an angle, when we integrate it, we just get sec of that angle. So it's going to be sec of a quarter x, or x over 4, plus my constant of integration. Cool, and we haven't done it for the previous 2 examples, but let's actually check that if we differentiate this, we will in fact get back here. So sec of x over 4, remember to use the chain rule, sec of an angle, if I differentiate it, I get sec of that angle times tan of that angle, sec of the angle times tan of the angle. Then I go inside and I differentiate x over 4. If I differentiate x over 4, it's a quarter, so that quarter comes out. Times by the 4, it cancels, so that's why I don't have a constant here. Cool, let's have a look at one more example. Just drag my table down. Let's have a look at this example. Okay, now in this example, I've got 1 over cos squared 4x. I go and I search, do I have a cos squared or a 1 over cos squared? And I don't. However, we know that 1 over cos squared 4x is just sec squared 4x. So I'm finding the integral of sec squared 4x dx. So I have a look here. Do I have sec squared of an angle? Yes. The integral of sec squared of an angle is tan of an angle. So, but then I see that it's composite, so it's linear. So I times by 1 over 4 to compensate. So 1 over 4 tan 4x plus my constant of integration.